Hello and welcome to a presentation on reducing multiple logic functions. So far we've been looking at single function logic, such as the two examples here. But what if you were asked to design a circuit that performs both of these functions? Individually, both of these functions are reduced as much as possible. But if you are asked to design a circuit that performs both of these functions, further reductions are possible by noticing that they share gates. By sharing gates, we can reduce the total number of gates used in the circuit, and reduce the cost and size of the circuit produced. So how do we go about ensuring that we share the most gates possible when reducing our functions? This first K-map is very restrictive in that there is only one best reduction. Trying to include the don't cares will just complicate the logic. The second K-map, however, offers us a choice. In a single function question, both of these answers would be accepted because they both use the same number and size of terms. However, in a multiple function circuit, we can choose the one that shares the most gates with the first function. Looking back at the first function, we can see it directly shares the CD0 gate with the second reduction of the second function. Therefore, this is probably the better choice. Also, if I rearrange the first term of the first function, we can see that it shares the A0 C0 gate. From this example, it's easy to see that the smaller the group on the K-map, the more logic gates are needed to create it. That's why we can take the large groups from the second function and add them to additional gates to get the small groups from the first function. And here I've recreated the circuit from the example. We can see that the CD0 gate here is shared between the two outputs, as well as the A0 C0 gate. Sharing those two gates allows us to have two less gates in the overall circuit and simplify the design. Let's look at another example. Hopefully you remember these two from my presentation on K-maps, and you'll remember that the reductions we got were as follows. In that presentation, I said that both reductions for F2 would be accepted, but once again, there is a better option if we're combining F1 and F2. Unlike the first example, it's not immediately obvious by looking at the K-maps which reduction is better. So let's take a different approach. Let's try finding the inverse of F1 by grouping zeros. We can see the inverse of F1 uses the same term as the first reduction of F2. Well, it's great that the inverse shares a gate, but how does that help us with the non-inverse? If we invert again, we can get the original F1, and some simplification reveals that we can still use the BD gate if we invert it. This will allow our functions to share gates even when it might not have been obvious from the start. Let's go ahead and quickly build our circuit here. We only need the two AND gates. The first one being B and D, and the second one being C and the inverse of B and D. And then we have our two outputs, one for F1 and one for F2. Since I have this all built out, let's take a second to talk about gate delay. Looking at our circuit, it should be impossible for both of the outputs to be high at the same time. This should be clear from the fact that output 1 is dependent on the inverse of output 2. However, if you pay attention to the outputs while I change the inputs, you can see that temporarily both outputs are high. This is because of gate delay. Gate delay refers to the simple fact that logic does not happen instantly. It takes time for the outputs of the AND and NOT gate to switch, in this case around 10 microseconds. In this case it doesn't really affect anything, but what if I made the assumption that both of the outputs would never be high at the same time? Or if I connected my circuit to another circuit where the output changed depending on if output 1 or 2 was reached first. That is what we call a race condition and will be the subject of a future video. But for now we'll just do a recap of what we learned in this presentation. So, when reducing multiple functions, Find the best reductions of the functions separately first. Compare the reductions to see if they can share gates. Remember that gates can be shared when the functions have the same terms, similar terms, here the AB gates can be shared, encompassing terms, here the BC gate can be shared, and inverse terms. A or B is the inverse of A naught and B naught, so we can share that gate. And remember that sometimes functions just can't share gates. And that's all for this presentation. I hope to see you next time.